Okay, so we are going to do ANOVA. Do take notes because the book has it, but it has a lot of formulas. And there's a specific convention that we use in ANOVA. That's what the authors are using. I don't want to do that in this part. We'll keep this part. So what is ANOVA? Got to start with executive. Let's go back. What is the purpose of a two-sample t-test?
To compare two means.
Two means. Okay.
Yeah.
And
what?
Two means of blank samples. Fill in the blank.
Dependent samples.
My heart just dropped. Is
Was
it
it-
dependent?
Yeah, you said a two-sample t-test. I guess it doesn't. I don't know.
There is another case. Right? Independent samples.
Yeah, I meant that. Come on.
Sure. So if you recall, a two-sample t-test is used to compare two independent samples. A special case would be the dependent sample scenario. And we saw two cases in the two independent sample test. What are the two cases? It has something to do with variance. Equal variances, unequal variances. If the variances are not equal, then we use Welch test. What if instead of just two samples that you get from a population, you have three?
Oh gosh.
Just seems crazy.
Or more. You could
Oh,
have 4,
God.
5, 6, doesn't matter. If you want to compare, how would you compare? Well, compare in the sense we want to compare means. In other words, is there a difference? Significant difference. Among populations, more than 2 populations. But this is a case where I have 3 of them. If you have to compare means, just using 2 sample t-tests, how would you compare? This scenario, even though you've got 3 samples, but you want to compare using 2 sample t-tests, how would you do it? You have to take a guess. Hint to you can also call it as
Two-tailed.
two-tailed.
Well, you said two, we're paired. So yeah, I'm trying.
How about this?
Yeah.
I can compare 1 and 2. Right? See if there's a difference. Compare 2 and 3. See if there's a difference. Then compare 1 and 3. See if there's a difference. Now, the issue with that is under the law, It is going to increase error probabilities under the norm. In other words, specifically, type 1. In addition, decrease power. Simply put, it's going to give you conclusions that are not proper. And this only happens under the norm. But our entire construct of hypothesis testing makes null the reference. So null is always where we're going to start. So if you start comparing using past, then error probabilities are going to go up. However, if the null is rejected, you are no longer under the norm, correct? In which case, you can do pairwise comparison. Good? With me? So, under the norm, I cannot, but if I reject it, I'm no longer defined by the null distribution, so I can go and compare 2 at a time. So, the problem is when to decide if I can move from the norm so that I can do a pairwise comparison, or how to decide. That is the job of ANOVA. Okay. So ANOVA decides, or the decision is to either reject the norm, which would simply mean the average of the first population is equal to the second all the way up to the case population. The alternative, any thoughts?
It's not equal.
Very bad.
Dang, I got it wrong.
Yes. It's not a good day.
It's not- We just said it was terrible. It's a tragic.
So I'll give you a hint. Phoebe got one of the options correct. So when she said not equal, replace all of those by not equal. Right. That is one of several possibilities.
Is there like a U1 equals U2 doesn't
U?
equal mu3? I mean mu, sorry. U1 equals mu2 doesn't equal mu3? Is that like a thing?
Exactly. So these two might be equal. It may not equal those two.
Okay.
Or all of these might be equal, and these three may not equal that one. Right? So you've got a whole lot of possibilities. So we don't have a direct alternative, rather we simply say either at least one of the means are different. Or there is a significant difference among populations. Populations, people also call them as factors, groups, treatments. I say tomato, you say tomato. Same thing. We are comparing multiple groups, multiple treatments, multiple factors. They all mean different populations. In my case, I have 3. So there, K would equal 3. But there is nothing wrong comparing a pair at a time. The problem is under the norm, when you do that, the power is going to go down. We talked about power type 1 error way back when, and if the error probabilities are high for a procedure, then that procedure is not reliable. So we can't do a direct pairwise comparison. So we want to see if that condition is removed. And if it is removed, I can move on to comparing pairwise. Good. How do we determine that the null doesn't hold anymore? We do an ANOVA first. ANOVA is going to tell me that there is a difference, which would mean you would reject the null. That the means are all the same. Yes. Once I make that decision, I can go and compare pairwise. Good. That is the idea. Okay. Let's see. Because of the nature on how the test is defined, in a sense, I can simply say that there is at least one difference, but I cannot pinpoint which is which. ANOVA is called an omnibus test. It can't pinpoint which means are different. All it can tell you is there is a difference. It is a global decision. That's what often we call it as omnibus. If you ever get a job in genomics, you will see that word time and time again. Omnibus. But for now, I know it's good now. Good so far? I want an example where we compare 3 populations or groups. If you want to give me 4, that's perfectly fine.
Is the word omnibus used in the same context as like collection of records? Omnibus?
Yeah, the same concept. You know, you are making a collective decision. Same thing. That's why I brought up gene expression, because it's a collection of experiments that you put together.
I've seen it used in politics for a bill that is like a bunch of things together. It's like an omnibus bill. In Canada, this is a thing.
Okay, whatever thing you gave me is the wrong example.
They just used the like word. It's like an omnibus bill. They were like, it had like.
Yeah, to collect, I see what you're saying, but
No.
doesn't give me an example. So I want a case where an experimenter or a researcher is comparing 3 groups or 4. Can you think of an example? Okay, go ahead. Don't Google.
What was the question?
You are right, by the way, Jonathan.
What?
It is. It works in the same.
I don't know, but this is for example, different university populations of the same like test.
Okay, standardized scores for different universities, 3 different samples. Now, are the samples independent? Yes. So, for instance, here, Harvard, somewhere in California, another university, you pick 3 universities at random, the scores, for example, in an undergraduate statistics course, they're all independent. So the samples are independent. Now that becomes a requirement for ANOVA. Cannot raise that part. Assumptions, requirements, the If the populations are independent, it will imply whatever sample that you collect from that population will also be independent. Of course, the samples are random, or must be random, and by now you should know what should go in that blank. What type of distribution should it have?
Normal.
Strike through today. Normally this.
Wait, I dug. I did know that. Don't worry, KJ.
I stopped worrying. I just gave up.
Oh my gosh, never tell a student that. We learned that in our
You know I'm
classes.
joking, Mark.
That's what he wants you to.
Normally this is and third case. Let's see. We sort of started this from a two-sample t-test, independent sample. So that has an important assumption. That will come here also. Any guess? Six.
Is it like xi is greater than yj or something?
That is not a two-sample.
That's what the rank stuff.
That's not parametric.
The two types of t-test, that is the hint.
Oh, so like the Welch's.
So what is that, Julia?
Variances.
Variances, what should be?
Equal or not equal?
Variances must be taken into account.
True. In what way? Do we want it
Equal
to be equal or not equal?
Oh, I don't.
If they're normally anyone. No, equal.
We want them to have equal variances. So if you have k groups, all k must have equal variances. That is an assumption. But one might say, well, there is no way we can get exactly the same variance. Do you agree? You're dealing with random procedure. So almost identical, good enough. But then saying almost identical is not objective, correct? What I think as equal variances may not appeal to you. And in science, we can't be making subjective decisions. Can I make this possible with you?
Yeah.
Go for it.
We have the goal, we have the assumptions. We can validate our assumptions. How do we validate? Typically, to determine normality.
Shapiro-Wilks.
You can use the Shapiro-Wilk test
Or a visual.
or visualization. The same will help in identifying variability. I'm going to address how. Visualization not only gives you or tells you whether the data is normally distributed, but it can also give you information about variability. Levine's test for equality of variances, or you can use a chi-square. That's funny Greek.
Which is a way of saying it's a deal. By the way, from my province stats exam, quiz. That was terrible. That was nothing like the worksheets I was given.
You can use a chi-square test for equality of variance. Oh, here is a question.
Oh, no, what?
Chi-square is a special case of gamma distribution.
I know,
What is alternative? Oh, sure.
it's the A minus, no, that's the
That's
uniform
one.
one. I could pull up my table, but I was also not given during my quiz until after I finished it, so.
It's okay. Two and K over two.
I'm a little salty about it, so I wouldn't really,
So,
I don't know.
oh, it's like it's the theta over two, right?
Yeah.
I didn't hear you.
two and K over two. You can either use Levine's test, or you could use chi-square test. There is an F version also. Whichever. Good.
So you can look
Oh,
up,
but when I said two and K over two, answers K over two and B test two, or we could have it as one half. That's for the record.
make sure you tell Pat how I've been connecting the information I've been learning.
Okay. Are you taking this semester?
Independent studies.
Oh, I see. Okay. Are we clear?
Yeah.
Yeah.
Okay. Starting with data collection, verifying or validating assumptions. These are the options that we have. Once they are satisfied, we go for an ANOVA. Erase this side. Yes?
So what do we use if the variances are not equal?
Every time.
You can't use it.
You can't, no, I know, but can you use something else?
Not wrong.
Okay.
We will get to it.
Yeah.
We will.
And there are newer methods that people came up with. Okay. What is the process and why do we call it as analysis of variance? If I want to say compare schools on an example, we'll use Jonathan's example.
The incorrect one.
Why would I use an incorrect example to explain it, baby?
Because he gave an incorrect example.
No, and then he gave a correct one.
Oh, I didn't hear the second part.
I was just talking about like omnibus.
Oh, like the word.
Yeah.
I'm gonna make boxes.
Oh, yikes.
Super.
Good.
Oh.
By the looks of it, do you think that the means are different?
Mhm.
Yes, no, maybe. They are different, but I can't simply say, well, I looked at it, they are different. Right? Doesn't work that way. Reason being, we have to account for the randomness of data. In other words, variability. If I collected another sample or conducted another study, we want to know the chances that we would end up with a similar conclusion. I'm going to write the standard deviation. Good. Those are the standard deviations. If you square them, you would get the variance. So square 1.22, 1.6, 1.8 to get the variance. Great. Do you think the variances are equal? I mean, mathematically, they're not equal, but statistically, they might be the same, right? Levine's test, chi-square test, Brown's test, there are a bunch of them. They will tell us whether the variances, even though they are different, whether they are statistically different or not, that can be answered with this. Good. what is the fundamental principle of ANOVA? It is called analysis of variance for a reason. So what should we be using to get to a conclusion? The variance. And there are two types of variances. Ideally, or nearly ideal. In order to reject the norm, I want you to answer, do we want the mean group variance to be large or small? Within group variance to be large or small? If I have to reject and conclude that these means are different, should I expect number one to be large, small, number two, large, small? Make one option.
Large.
Can we vote?
Voting isn't good.
We don't do that here.
Why not?
Large or small? Large or small?
Okay, we'll start with one. I want to reject, or if we are rejecting the norm, then the means are different. Think people. Well, very good. So the answer here, is large, small. Mind you, this is like an ideal or near ideal case. So if I'm rejecting the norm, that would simply mean the means are different. That would mean the variability between these three means must be large. Do you agree? And I want each sample to be consistent, correct? So the within variability within each sample must be as small as possible. Agreed? That is the ideal case. Based on that.
Was that impressive? My answer?
Oh.
That was impressive, wasn't it? My answer.
Very good. The non-distribution is,
Gotta dole out some compliments along.
let's say,
with it.
problem stance. What is the distribution of variance?
I left that in last semester.
Typical distribution of variance if normality holds true. Let's add that. Uniform.
Yeah, can it change throughout the?
That's a negative on that one.
I'll give you a hint.
Yeah.
Uniform is a trivial distribution that has a lot of uses, but uniform that is useful is on 0, 1, because probability is between 0 and 1. That is probably the only case where I would put any meaning to a uniform distribution. Anywhere else, we teach it so that you understand what a distribution is. By all means, it's a trivial distribution. Well,
It's normal.
could,
Normal.
read my mind, could it be normal?
I don't know, I just don't understand why the variance would be normally distributed. Like, is it between the different samples?
No, in general, variance. what distribution?
Give me multiple.
He's just gonna, okay, I'll give you a hint.
Okay.
The hint is to my left. Jonathan, did you have a question?
I was gonna ask something, but they were talking, so I forgot.
Scott, okay.
Sorry, gamma.
Oh, yes, what kind of dog?
Chi-square.
A chi-square.
Spelled
So
C-H-I.
easier way to remember, squared, squared,
Oh, variance.
that's
Squared.
standard deviation squared. So if the distribution is normal, typically the variance will be distributed with chi-square distribution. So I'm going to come up with a ratio.
Could tell you, don't ask me. Clearly, problem stuff doesn't strong. All time.
So,
Large K.
Here is my ratio. And numerator between variance, denominator within variance. In an ideal case or near ideal situation, we need to have the numerator between variance to be large, denominator within variance to be small, right? Ideally. That's it. If I'm going to reject the null, should the ratio get bigger and bigger and bigger, or should it be smaller and smaller and smaller? Bigger, okay. So ideal, near ideal case, rejecting the null between variance has to be large, within small. The numerator has to be bigger than the denominator. So if I get a large value for that ratio, I will reject.
You will.
Good,
How large is large enough?
we'll get that. Not yet.
So the null distribution is.
I'm still explaining the process, but
Right. The null distribution for it is chi-squared, right?
no,
No, the more. Okay.
getting there.
Oh.
I see the excitement. So that's
Very
good.
cool. Negotiate, like,
Proud of you. Variance has a distribution chi-squared. If you recall the formula for variance, what is in the denominator? You have to divide by something, right? You find the deviations, you square the deviations, you sum them all, and then you divide by something.
At big N.
Big N,
No, it's the
Square root of
1224. It's the 1224 one, right?
And minus one.
very good, oh my. Denominator
Yeah.
is
Big
N
N equals
minus
-1.
1. So whatever value you divide by would be what goes here, and I'll tell you what that is. Denominator will be N minus K. Good. Again, I won't get into the maths of this part. Whole lot of distribution theory, which we don't even cover until we get to part. So, where does these two, or where do these numbers come from? That is what you would divide the square deviations by to find the variance. Same here. I don't want to put equal to, I'm going to put quickly. What does that mean? 3162.
Yeah, I know, but I don't know exactly what it means.
What does that mean? Equivalent?
Almost.
Isn't that the two squigglies?
That's the two squigglies.
Make it strip.
Isn't it used for like, that's the distribution or whatever?
So this ratio is distributed as that. Good. Okay, well, I don't know if you guys did it in problem stance. What is the distribution? The ratio of two chi-squares. Ratio of two
I
chi-squares.
do a transformation.
You can't, you know, how do we derive stuff? You do transformations, all kinds of things to come up with the distribution. But do we know what that distribution is? No.
That's all we're,
We're about to F it all up.
oh, it's the
Yeah,
distribution.
it's
We just, we derived that at one time.
Oh, you
class.
derived that?
Oh,
you
yeah.
did do that.
It's like a whole
Yeah,
class.
right. Yeah, it's pretty hour. It was the whole class, no intro or outro.
That's right. It just starts with spontaneous, he was writing on the book.
It will show up on God's school. K minus one, N minus K. Good. The ratio of two variances, which chi-square distributions, will be an F distribution.
If you derive the F distribution,
Is that
if you derive it from this, or is this the only derivation of it?
Yes.
Do you remember that? Do you remember if you started with this?
I feel like we started with the T distribution or something.
So,
I don't know, I think it's
so T distribution also has a derivation. If you recall, too much. But if you recall, x bar minus mu s over square root of n. Yes. Denominator is square root of variance. Correct. So you've got a transformation in linear one for a normal denominator variance. If it satisfies that form, it will have a T distribution. So that is another derivation. It's not as time consuming as F, but it is not easy. Will take time. But I'm glad you brought this up. When we did the T test, one sample, what was the degrees of freedom? N minus one, right? Why n minus one? The variance, when you calculate the variance, you divide by n minus one. Yes? Okay. Degrees of freedom, what you divide the variance by. Here I said variance, but when variance, in computing this, you divide by k minus one. So what is k minus one? Degrees of freedom. Okay. Since it is in the numerator, some textbooks would refer to it as numerator degrees of freedom. Some would call it DF1. DF2 would be the denominator degrees of freedom. Good. So all of this would work under the assumption of normality. If the data is normally distributed, you do that transformation, you will have a T distribution. If the data is normally distributed, you find the variance, it will have a chi-square distribution with that degrees of freedom. If the data is normally distributed or within variance chi-squared. In general, variance will be distributed as a chi-squared as long as the data is normal. Good? Okay. Since the distribution is F, we call the ratio as F ratio or F test statistic. So ANOVA test statistic is simply F. Having said all this, what is the null distribution? For a t-test, it was t.
F.
Very good. So the null distribution for ANOVA is an F distribution. It has two parameters, first degrees of freedom, numerator degrees of freedom, second degrees of freedom, denominator degrees of freedom. We still haven't addressed what n is. Any guesses?
Populations combined.
Observations?
Is it-
No, like the samples. Populations,
It's a specific word.
samples.
Sample size. So it's the sum of all sample sizes. K is the number of groups. Good. So if you add the sample sizes together, you will get n, and k will be the total number of groups. Normal distribution is symmetric, do we agree? A standard normal is symmetric, centered at what value?
0,
0. Standard deviation?
1,
1. Okay. In other words, it can't be negative. Could this ratio be negative? Jonathan says yes. Let me ask again. Could that ratio be negative?
No, because you're squaring the variance.
Very good, Vic. Not squaring the variance.
Well, you're squaring the
the
standard
standard
deviation. It's squared.
It's a square, right? Chi-squared. Square, never negative, never negative. The entire ratio will not be negative. So the distribution will only be on the positive side. Do you agree? Which will give us this shape. Twenty 23. Blackwood,
Tail.
right tail, black stew.
I squared tail.
I always mess up the duration.
I was getting into it.
A chi-square distribution is also right-hand. Going back 15 minutes or so, we wanted the numerator to be bigger than the denominator, ideally, if we have to reject, in a way. So I want this ratio to get larger and larger, correct? As it gets bigger and bigger, it is going to go this way, yes? So if the rejection region is only on one side, that will be our type 1 error probability. And this is our cutoff point. If your test statistic exceeds that cutoff, you will reject. Otherwise, you don't reject. Given all this, is an ANOVA a two-tailed test? No. Is it a left-tailed test? No. It is a right-tailed test, always. Good so far? When you do an ANOVA, no matter what software you use, I don't use SPSS. I'm a programming nerd. I don't like, I mean, I know SaaS, but I don't like using SaaS. I use ARM. Or
I would have never guessed.
right?
I like art.
Regardless of the software, even Excel can do this. You will get a table when you do an ANOVA. And the structure of the table doesn't change often, but the terminology, they'll use different words. I'm just going to go with between and within. What is the degrees of freedom for between? No.
Oh.
K minus one.
Minus one. Within n minus k. Add them together, you will get n minus one. Right? If you think about it, you combine all the samples together, excuse me, yeah, okay. Combine all the samples together, in other words, put all the observations together. In total, you have n observations, uppercase n. And if you find the variance of all those observations in that formula, the denominator will be n minus one, uppercase n minus one. Do you agree? That's why this is coming from. Good. The next part is FS.
Wait, FS or SS?
SS. So going back to 2023, earlier today, variance is simply sum of squared deviations divided by n minus 1, k minus 1, n minus k, right? So the numerator part of the variance formula is sum of squared deviations. I just call it B for short.
Oh,
The degrees of freedom for the sum of squares is k minus 1. Yes. So the numerator if you have a sum of a bunch of values, you divide by the total number, what do you call it? Mean. So MS stands for mean squared.
It's kind of annoying because we use capital M for median and the other.
yeah, why don't we use mu?
Yeah, honestly, I agree with Phoebe, which is
I
Wait, what do you mean
disagree
shocking?
completely.
US is so gross.
Okay, so
Yes.
just because you see okay 7 doesn't mean median everywhere.
In my mind.
Well, we know that now.
I'm glad. That was the time. That is the same
US
as
is disgusting. The way it goes.
variance for the between case. S squared, standard deviation squared, variance. Over here. Sum of squares fall within. To find that, we will divide by n minus k. ms w, which is nothing but the variance of that group. Good. We are taking the ratio of those two. Between variance, within variance. So over here, a software is going to give you SSB, there, SSW. The corresponding mean squared, that value over that one, MSB, MSW. Yes. How did we find the F ratio, F test statistic? We divided between variance by within variance. So that's over that, going back there. And that will be the table that you will see. So the logic is we want the between variability to be as large as possible so that you reject the norm. The more variability that you see between the groups, the greater.
So the F there, is that for like just between up at the top there, or is that for both of them, or
The entire expression.
that's for,
Yeah,
Okay.
so over here, I call F to be the ratio of between over within variance, SP's wide or over SW
okay, I
squared.
was just getting a little confused because it was in that between column.
It
so I
should
was
be
just
its
getting a
own
little-
little table.
Well, we can make this simpler, I guess.
There you go.
No, no,
That
no,
means
no,
that-
that means
No,
way worse.
erase the line underneath the
Yeah.
F.
Just get rid of it.
Now you're
just
like
under
directly
F.
Under
defined,
F,
goes
that's
into
it.
Which one?
F,
Like under the F,
yeah,
in the
but over
F
there,
row.
yeah, yeah,
or column.
there we
yeah.
go.
And then I'll put that.
Yes.
And
Yeah,
then-
oh.
Yeah.
You're missing one. Oh, okay.
So what's the point of the total?
We'll get that.
Oh, okay. Well, you look-
SST is the total variance. When we do an example, I'll go through that. The total variability would include variability that comes from between groups and within groups. So the logic is if I divide these two and if it gets larger, then it implies that the means vary a lot. So you will be rejecting the norm. Variance always chi-squared. There are some details that are missing here. There is a specific form in terms of variance. Up-level courses graduate school, you will see as to what that expression is. Not here. So ratio of chi-squares, I'm telling you that it will have an F distribution. In this case, numerator decrease to freedom k minus 1, denominator n minus k. Often, including R, will give a p-value. If it doesn't, we can find that p-value. It's not that difficult. I'm not going to ask you to find p-values. So, in practice, we get the groups, we verify assumptions, we just put it in the software, it will give us this table. We look at that table and we make inferences. That's it. Good. We still don't know as to which two groups are different. Correct? If I rejected the null, I don't know if one is different from two is different from three. I erased the example I had. Do we have it? So in that example, let's say I rejected the null. All assumptions were true, validated, and I rejected the null also. If you have to place a bet on the groups that differ in means, which two groups do you think will differ?
1 and 3.
1 and 3, what about 2 and 3?
Probably a different, but 1 and 3. Oh, never mind. 2 is less. Okay. Yeah.
Right.
2 and 3.
So I'm thinking 1 and 3 different, 2 and 3 different, maybe statistically 1 and 2 not different. So rejecting the decision to reject null in ANOVA came from 1 and 3, 2 and 3, but not 1 and 2. Good. That would be the next step, which is called a post-hook comparison. I will not get into the theory of post-hook comparisons or multiple comparisons. We will use Good.
Okay, so you said 1, 2, and 3. How come not 1 and not 1 and 3? No, not 1 and 2. Were you looking at the mean or the standard deviation?
Mean. We are comparing means.
Oh, yeah, you're right. Okay, I got it.
That's
Wait.
like what, at 9 o'clock? An hour ago.
I know, I forgot.
Well, you're doing some reading today.
Okay.
Reading assignments for Tuesday. Yes. Everything that we did today, you need to have a good grasp of. Your textbook has a chapter called one-way ANOVA. I believe it's chapter 4. First few pages of that chapter, in the first few pages, have a description on that table. They have formulas. Ignore them. Not in this course. We are going to make inferences using algorithms that we get from R. Before you come back, read, understand. Good. We are going to go directly to R next time.